All right, welcome back, everyone. Let me talk about the calendar that you guys have inside your packet here. I'm going to check pages 13 through 16 from packet 2. I'm going to do that by near the end of class. It's still coming in, so I'll do that at the end. But packet 1 and 2, classwork and homework, that's going to go towards your FRQ test grade. So once I get that checked off today, I have your test graded. I'll be able to add those points together and put it in the grade book. Hopefully later today, this afternoon or early tomorrow. Okay, so we're going to start our third packet, and we have an upcoming quiz next Tuesday. Okay, the quiz will just be 2 FRQs, which is going to be Riemann sums and differential equations. So, and again, this quiz grade will be buffered by your homework grade or homework classwork grade. So, packet 3 is going to be worth 50 points, and then your quiz that you take in class will be 50 points. Add that together, it'll be 100 points quiz grade. Yesterday, we started particle motion Riemann sums. So we worked through pages 1 and 2. Yesterday, I had that recorded on my in the video on my website, but you also have the key in front of you. So again, at the end of the class, I'm going to check pages 13 through 16, and then today we're going to work on pages 3 through 6, and whatever we don't finish. You guys finish for homework, and then I'm going to check pages 1 through 6 tomorrow. Okay, I'll send out a reminder this afternoon. Right, so I'm also inserting some grade in, grade out anti-derivative word problems. It's not going to show up on the quiz, but I want to continue to have us feel more comfortable with these types of problems. So we're still going to go over it inside packet as review. But I think after we get through Friday and Monday, we should feel pretty good with these 2 topics, since we'll be going through many problems over the course of this week. So our quiz will be next Tuesday. And then after that, we're going to be working towards our multiple choice test. And our multiple choice test will be split up into 2 days. It'll be 30 minutes that Tuesday of EOC, and then Friday of EOC. So Tuesday's going to be a full class period, but it's only going to be 8 questions. But you have a full period to work on it. This one is also 30 minutes. Same number of questions, but maybe a little bit less time. It'll be like 45 minutes or so, since there is an EOC on this day. But the first multiple choice portion will be just over first semester topics. So when we get packet 4, we're going to be working through first semester topics, getting comfortable with those. You get to use your calculator. And then after that, then Wednesday, Thursday, we'll review second semester topics. But I think just working on FRQs in general, FRQs make generally second semester topics. So we're kind of more comfortable, I think, with second semester topics since we've seen them more recently, and we're also, the more FRQs that we do, the more practice we're just getting with second semester topics. FRQs are typically second semester topics, so we'll have 2 days to just do some more multiple choice review, and then that Friday will be your multiple choice test. So this is how the points will break down. Packet 4 will be worth 50 points. First part will be 25 points. This is 25 points. Add that together. That's 100-point test grade. And then that's going to lead us to May. And in May, we have 2 weeks before our AP exam. Our AP exam is going to be on the 13th. So that first week of May, we're just going to be working through packet 5. Packet 5 will just be the most recent FRQs that were given in the past 5 or 6 years. It says I have updated this, but I'm going to be checking packet 5 each day, and that will be going towards a quiz grade. So just completion grade, going towards a quiz grade. I'll also give you packet 6 as well if you want to work on packet 6, but we'll spend time May 6th through 10th going through packet 6. Packet 6 is just a combination of miscellaneous problems as well as multiple choice questions, multiple choice problems, and then packet 6 can be turned in anytime after the AP exam, or if you want to turn it in on the 10th, you can as well, since this is the last day for seniors. But you can also send it to me through Remind or through email that you completed, so I can give you credit. So packets 5 and 6 will each be worth quiz grades. Okay, 100-point quiz grades. Okay, so that takes us to the end of the school year. Any questions about our calendar? So yesterday we worked through pages 1 and 2. So I'm gonna skip those for now. Maybe I'll come back and highlight some of those steps. But let's start with number 3. Here are some good reminders at the top, some particle motion reminders. Let me highlight those, and then we can look at this problem here. So we know velocity can be thought of as the rate of change of position. You can think of if x of t is position and x prime is velocity, or dx over dt. Acceleration is the second derivative of position, but you can also think of acceleration as the first derivative of velocity. So v prime is acceleration. But we can also go the other direction, right? We know that position to velocity to acceleration, that's a derivative relationship. From acceleration to back up to velocity, back up to position, that's going to be an integral antiderivative relationship, right? So the integral of acceleration will take us up to velocity. Integral of velocity will bring us up to position. Total distance is accumulating all your velocities over a period of time. Okay, and total distance, the absolute value is around it to indicate that it doesn't matter if we're going left or going right. Doesn't matter which direction we're going. We're always going to be accumulating distance, and that is going to we're going to count every velocity or every accumulation of velocity as positive distance towards a number. So not displacement. Displacement is just the integral of velocity, but total distance is the integral of the absolute value of velocity. Okay. Right, average velocity. I think this is average value theorem. 1 over b minus a integral of v of t. You can also think of average velocity as the change in position over change in time. X of b minus x of a over b minus a. Average velocity is the change in position over change in time. So yeah, so we can think of it in 2 different ways. Average acceleration is the change in time. So we just have to understand that if we see that word velocity and average, we're not touching velocity function, we're touching the function above it. It's the slope of the function above it. Average acceleration is the change in velocity, so it's change is using velocity. Even though acceleration is in the name, we're only using velocity to get to average acceleration. We also use this quite a bit, where if we're looking for a final position, it's equal to initial plus displacement. And then displacement of velocity is the integral of acceleration. This is also a first theorem application. And in terms of increasing, decreasing speed, we have to know that to determine increasing or decreasing speed, we have to compare the signs between velocity and acceleration. If velocity and acceleration have the same signs, then increasing speed. If they have opposite signs, then decreasing speed. And then increasing velocity is where acceleration is positive. Decreasing velocity is where acceleration is negative. Okay, so let's look at number 1 here on page 3. Okay, this is going to be a calculator question, so we can have our calculators out. A particle moves along the x-axis so that its velocity v at time t greater than or equal to 0 is given by v of t equals sine of t squared. The graph of velocity is shown between 0 and root 5 pi. So this is not the position function, this is the velocity function. The position of the particle is x of t. And then we know that there's an anchor point here. At time t equals 0, the particle is located at position 5. Okay. Again, this is not the position function, so that's why this doesn't look like x of 0 equals 5, because this is not position function. So part A says find the acceleration of the particle at time t equals 3. So acceleration is the what of velocity? Slope or the what? Derivative, right? So if I want to find a of 3 is just going to be what? V prime of 3, right? And we can use our calculator for that. I mean, we can do this by hand. I guess we can. It's not too bad to derivative. We can make this cosine t squared becomes cosine t squared times 2t. We can do chain rule there, or you can do math 8 and then just make the calculator do it for you. We can do d over dx. Type in your velocity function. So the calculator is going to find this derivative, and then it's going to plug in 3 for you to get from velocity to acceleration. Okay, find the total distance. What's our formula for total distance? Integral of the absolute value. Yep. Total distance. Yep. So we can just go ahead and just do math 9. Okay. To get to your absolute value notation, you can do math number ABS. Yeah, and I have it up on the board there. Absolute value is math number ABS. And then type in your velocity function. Okay, total distance is 1.702. Units. Part C says find the position of the particle at time t equals 3. So we want to find the location of this particle. We know we have a starting location, so we're going to use this formula here. Final equals initial plus displacements. X of b equals x of a plus however much progress we want to make between those time intervals. I'm just using this formula there to arrive at my final location. Okay, we can enter this in our calculator. Math 9, type in your velocity function. Okay, part D. Between 0 and √5 pi, which is over here, find the time t at which the particle is furthest to the right. So we're trying to find the furthest points. So what theorem are we trying to apply here? Yeah, he's trying to find maximum, minimum, furthest left, furthest right. Any extreme locations that we're looking for is always going to be extreme value theorem, which means we have to find endpoints and critical points. And critical points is where our velocity is equal to 0. And so
Sine line.
yeah, sine line. Yeah, so we know that this is where our graph is going to experience positive velocity, negative velocity. We want to look for velocity equal to 0. So we have 0 and √5 pi, and we can find these other points as well. Okay, there's two ways that we can do this. We can put it in our calculator and find those x-intercepts. Okay. And then do second trace 0, and then find those x-intercepts. Another way to do this is recognizing that we can just use unit circle values to get those values. So sine of t squared is equal to 0. And if I did sine of t squared is equal to 0, that's the same thing as saying t squared is equal to inverse sine of 0. And then if we list out all the places where sine is 0, we know sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, 3 pi, 4 pi, and then 5 pi is our endpoint, right? If we take the square roots, then we can also find all these decimal versions in our calculator by doing second trace zeros. But I want to show you another way to do it is you can do it by hand as well. So that means this is 0. This is root pi. This is root 2 pi, root 3 pi, and root 4 pi. Okay, in our calculator, we would go to type in our velocity function. So y equals sine t squared or sine x squared. And then do maybe zoom 6. Yeah, that's a little too far in. So what we can do is you can do second trace, or we can do a window here. Let's just go from -1 to, now root 5 pi is probably around 5 or 6. Let me do from 0 to 6. Just picking some numbers here. I guess I could also do a zoom box around that region there. You can find all these x-intercepts there. We do second trace 0. So I can pick a point to the left of the x-intercept, hit enter. Pick a point to the right, hit enter. So 1 point. Now, if you get that 1e -13, that's basically 0. It just didn't round to 0, so that just feels like a weird notation, but that just basically means it's really close to 0. Consider it 0. And then 1.772. So 1.772 is about the same thing as root pi. If we look at our sine line here, we know above is moving to the right, below is moving left, and it's going to keep alternating, moving left and right. Now we're looking for the furthest right, so we only need to test what points? Obviously the endpoints. Yeah, basically the maxes, right? So root pi, we got to test. Root 3 pi, we don't have to test root 2 pi and root 4 pi. I mean, we can. We're just doing additional work that we don't have to, but we definitely need to test endpoints and test our relative maxes. Okay. And if we want to find the position, then we go through our final equals initial plus displacement for all of them, and then we compare the y values. We know what x of 0 is, so we'll do x of 0 plus integral from 0 to root pi. And then from 0 to root 3 pi, and then from 0 to root 5 pi. Okay, so here's the work involved here. And all that can just be entered into the calculator, and then we compare between our endpoints and our critical points. We're looking for the one that is furthest to the right, so the largest value. That's 5.895. So we know particle is furthest to the right at position 5.895 at t equals root pi. Any questions? Okay, let's look at page 4. Okay, page 4. Velocity of a particle moving along the x-axis is modeled by a differentiable function. So we kind of visualize what's going on here. This particle is only moving on the x-axis, so it's only moving left or right. So left would be negative velocity, right would be positive velocity. If it's 0, that means it's not moving. Differentiable function means it's a smooth curve, no sharp turns. Okay. T is measured in seconds. Selected values of T or V of T are given in the table above. Particle is at position x equals 7 meters when t equals 0 seconds. So that's kind of like an anchor point for us to use later on. Estimate the acceleration of the particle at t equals 36 seconds. So it says estimate, so we're not going to use calculus here. We're going to use algebra. How can we estimate acceleration if we have the velocity in front of us? Well, derivative, if we had a function, right, but slope, right? So slope is our next best option if we don't have a function to find the derivative with. So, but what information do we need if we want to do slope? Which points would you choose? Yeah, closest to the target or closest to your target time is going to be your best bet, right? I mean, you can choose other points as well, but you're not going to get as good of a estimation. So the best estimation is going to have to come from 32 and 40 because these are the closest points we have to 36. So we do change in velocity over change in time. And that'll give us our acceleration. What do you think our units of measure will be? Meters per second. Yeah, meters per second per second. Yeah, meters per second squared. Okay, all right, try that. So acceleration at 36 seconds is roughly the change in velocity over change in time. So 7 minus -4 over 8, so 11 meters per second squared. So acceleration is increasing at a rate of 11 over 8 meters per second squared, roughly at that moment. Part B, using correct units, explain the meaning of the depth integral from 20 to 40 of v of t dt. So if we use first theorem, what does the integral from 20 to 40 v of t turn into? How can we rewrite this? What's v of t going to turn into? Position. So it's going to be x of what? Yeah, x of t, and then we do what with the bounds? X of 40 minus x of 20. Right. So what is x of 40 minus x of 20? What does that mean? That means the particles change in what? Position, yeah. Change in position over that time interval, yeah. It's asking then to approximate that using trapezoid. So remember, trapezoid rule is, or trapezoid area formula is 1/2 width, height 1 plus height 2. So we do that 3 times for each of our subintervals here. So our width is 5 because we subtract our t values, subtract these to get 7, subtract it to get 8, and then we're not going to change this. It's not asking for total distance. It's asking for displacement. So we're going to keep these negatives there. So we'll add the 2 heights for each of our each of the areas. So width over 2, height 1 plus height 2, width over 2, height 1 plus height 2, width over 2, height 1 plus height 2. So it's okay to have negative displacement. That just means that you're going to end up, that this particle is going to end up to the left of where it started. That's all it means. So it's okay to have negative displacement. So 1/2 width, height 1 plus height 2. Remember that even if your interval spans across multiple order pairs, every area is only going to use 2 heights. So even if it spans across multiple heights, we're not going to add up all the heights. You're just going to add the ones at the end where the bracket is going to point. Okay, part C, between 0 and 40, must the particle change direction in any of the subinterval indicated by the data in the table? If so, identify the subintervals and explain your reasoning. So can we tell that this particle is going to change direction? And what indicates that there's a change in direction? Change in signs, right? So we know that somewhere between 8 and 20 seconds, it's got to change direction at least once. Maybe there's hidden data that we don't see. Maybe it changes direction multiple times, but we know there's at least one change in direction here, right? To get from 5 to -10, it's got to cross through 0 at least once. And then is there another place? Yeah, 30 to 40, there's at least one direction change here, right? It's going to go left and it's going to go right. So to go from left to right, it's got to change direction to do that. So somewhere in this time interval, there's going to be at least one. And what is that applying here? We're applying what? What theorem is that? Intermediate. Yeah, intermediate value theorem, right? That's where we can guarantee that, if I have a number lower than my target and a number higher than my target, then, and I know it's continuous, I know my target is going to be reached. My target is 0. I'm trying to cross over to 0 so that there's a change in direction. It's only going to change direction if it hits 0, and on both sides of 0, there's a positive and a negative. Okay, so particle change direction. Since V of t change signs in each of these respective intervals. Okay, part D. We always can kind of expect this to happen on your FRQs, that part D or part C or part D of your FRQs is always going to feel a little more challenging. You want to kind of give our best effort, but it's not like, oh, we got to get part D right in order to do well on the AP exam. We just have to kind of do what we can to earn as many points but just understand that it's always going to feel a little more challenging on the last part of your FRQ. Any questions though, A through C? Okay, let's look at part D here. It says, suppose the acceleration of the particle is positive between 0 and 8 seconds. So what does that mean in terms of how the graph is going to look? Positive acceleration, what does that mean? That means your velocity graph is going to look what? Your velocity is always going to be increasing. Yeah, it's always going to be increasing. Between 0 and 8 seconds, though. Okay, it doesn't say that after 8 seconds. It doesn't guarantee it, but between 0 and 8 seconds, we know that our velocity is continually increasing. We see that hinted at this with this table here, 3 to 5. That means between this and this, it's always increasing. It's not going to ever dip down. It's going to go from 3 to 4 and continually rise from 4 to 5. Okay, so we know that our velocity graph is continually increasing on that interval. Explain why the position of the particle at t equals 8 seconds must be greater than x equals 30 meters. So we know that the position is the what of the velocity. If we're looking at the velocity graph, position is going to be the what of that. Antiderivative. What's a visual way of doing antiderivative? It's the what of the velocity graph. Not slope, but the what? Yeah, if we want to accumulate velocity over time, that will give us our displacement and this area, right? So we know that at 0, the particle is going to start off at velocity 3. And then at 8 seconds, it's going to be all the way up at 5. Okay. And so the graph may look something like this. Your velocity graph may look something like this. It's saying, how do we know that this particle is going to be further than x equals 30 meters? Well, let's just see if we can find the area here. Maybe we don't know what the area of this is, but what we can do is we can do an area of this, right? This is easy to find. If we can show that this area will meet what we want to get to, then we can guarantee it, right? Because we know that whatever we get here is going to be less, it's going to be under approximating the area. It's going to be a safe area zone, right? So what's the area here? $24, right? So that means we know that over this 8-second period, this particle is going to travel at least 24 meters, right? More than that, because we know there's a gap that we're not accounting for, but there's 24 here. And it says, how do we know that x is greater than 30 meters? Okay, so we do know is that x of 8 is equal to x of 0 plus the integral from 0 to 8 of v of t, right? And we're approximating here. We don't know what this exact value is, but we know that this is going to be more than 24. So x of 8 equals, we know x of 0 is what? 7. So 7 plus 24, what's that equal to? 31. So we know that this particle is going to be further to the right than 31 because we're under approximating, right? It's more than 31. If it's more than 31, then it's definitely going to be more than 30. Okay. So since our position at 8 is already guaranteed to be more than 31, and x of 8 is greater than 30, since positive acceleration guarantees velocity will never fall below v of t equals 3. Right, so this part D is testing us to see if we understand that to get to position using velocity, we have to involve area, right? If we don't have the function in front of us, we can't take the antiderivative. we can visually, we can still approximate using area. We can, we don't know what that curved missing region is, but we know that we know for sure it's more than 24. So we use that as our anchor to make our argument. Okay, let's spend 5 minutes more, see if we can try number 5, and then I'll come around and check your packet 2, the last few pages from packet 2. Okay, part A, estimate f prime of 4. We have a function that's twice differentiable for all real numbers. We know it's a smooth curve. Table above gives the value of f, so f prime of 4, we can just find the what of the function. Slope, yeah. So which points would you choose?
2 and 1.
I would choose 3 and 5, right? I think this is a better option, even though 2 and 5, even though that isn't an approximation. 3, because we have 4 landing between 3 and 5, we want to choose these closest points. Now, if it was asking for f prime of 3, then that gives you some options. Then you can choose these 2 or even 2 and 5. But because 4 lands between 3 and 5, we want to use that 3.
Oh, my bad. I was thinking the f of x is types.
I see. I see. Okay, so f prime of 4, just the slope between the 2 endpoints. Evaluate the definite integral from 2 to 13 of 3 minus 5 f prime of x dx. Now, how many problems do you see here? Can you recognize this? What if we were to split this up? Would this be easier if we were to split this up into smaller problems? What if we did this? Okay. Same problem. It's just now we can just treat it like 2 individual rather than trying to think of, oh, this is just one big problem that we have to solve. Right. So if we look at it from this perspective, how would you handle this one here? What's the how would you do definite integral if it was integral of 3? Yeah, power rule and then upper and lower bound, right? How would you handle integral of f prime? Yeah, this is first theorem, right? So this is a functional relationship. This is actually applying power rule, right? So we know that integral of f prime is just f of b minus f of a, right? But this, we can actually apply the integral rule. 3 becomes 3x, and then we plug in 13 and 2. So 3 becomes 3x. We plug in the upper and lower bound. This is a separate process. F prime becomes f of b minus f of a. And then we start to use our table to evaluate these into numbers and then combine all that to be numeric value. And then we'll end with part C. Part C is just left Riemann sum, so that's pretty straightforward, right? We split our interval subintervals up, and then we do width times height, and we pick the left height for our subinterval. Okay, so if I can come around and check your pages 13 through 16 from packet 2. Okay. I didn't have enough coverage.
Yeah, I really made it towards the end, but then it was also like 3 AM. I guess I was ready to quit.
That's
Just be careful when you open it up because I wasn't able to like along the tracks, there's like a line through the middle, and I've edited everyone's volume to kind of fade in and out based on how loud or soft they were.
Okay.
But I didn't know how to make it go away.
Yeah.
So just like be careful you don't click on it or else it'll like.
Okay, that makes sense. Did y'all get all of y'all just like mine and stuff?
It kind of sounds like
Yeah. Oh no.
It doesn't sound like it's not like, or the music video, it sounds good, but like listening back, I'm probably gonna like.
Oh yeah, it's gonna be great. Yeah.
Well, this is
But at the end, like, like that. And then it just like, she just holds it and then it fades out.
That's crazy.
We called it play like trash.
Oh,
So Mr.
no one's ever done that before.
I don't know if it's idea that one. We're gonna lose all our points on it.
Yes.
There's one, it's gonna be this.
There was a class evaluation one this time. Class evaluation.
There's 6, there's 5, what, there's 5 other popular columns. It's gonna fall out, there's 5, yeah, we're all just gonna give each other a.
Yeah, for real.
Yeah.
Yeah.
Like, I'm not like. That's what I'm thinking about, wrong.
Yeah. What, you finished with the graphic or something?
Literally what I.
Really? Okay.
I have one more.
You don't finish them.
Shut up, I'm like, up till 3 AM, but that's all. Yeah.
Why'd they stick you with the?
What?
Why'd they stick you with the? I have to do it. I'm gonna check pages 1 through 6 tomorrow.
I was holding the
And
computer,
packet
like, recording, and then like.
6 homework.
Pages 1 through 6, yeah.
What are this, other than the last?
Maybe it's called the code school. But built matchup and putting it and so like right here, like these are can't find that anymore.
Got it.
So there were 2 years in the answer like it was and then like I just assumed it was the same thing.
I know. Okay.
But I got like one of them we should not like the last thing wall like I moved it, but yes, we're not.
Oh, okay. That's just, circle it. Yeah. I'm gonna ask the parent. Just like,
Yeah, and then, yeah, there's like a couple, and then there's still like more than that. I couldn't find it.
okay. So I'll be able to reach out to the people that's part of that. So I appreciate it. And then,
The numbers of ones that I've done, I've done like 7.
Okay.
And I realized, because you have to really change to all finish those. But the fourth
I didn't. Yeah.
You got one.
Yeah, that's like,
Those are kind of funny.
he's animated, right?
Yeah. If I